I really think that computation or compute will be one of the fundamental currencies in the future. I mean, it's already that, but even more so. It will become even more so.
Last week I was in Zurich to visit 2 for AI Labs. Every single month they have a physical meetup.
General idea is to talk about recent research, meet other cool people.
This was Jonas Hübotter. He's got a paper out talking about test time inference or transductive active fine-tuning. Think about the Google Maps analogy. As you zoom in, you get more and more tiles, you get more and more resolution to suit the specific situation that you're interested in. And that's what he's done for large language models. So essentially you get a test example, you do retrieval, and then you fine-tune the language model and you get significantly better results for that situation.
You have some problems that you're interested in solving, and instead of trying to solve everything, every possible problem at once, of course, if you could do that, if you could solve every possible problem at once, you would also solve the problems that you're interested in as a byproduct. But I mean, that's infeasible. We have limited time, limited memory, limited compute. Now, instead of doing all that, just focus on the problems that you're trying to solve, actually, on the problems that you're interested in. And most likely you can do that much more efficiently than if you were trying to solve all problems at once. The DNA in our form of life gives us some very hard constraints, right? We have to consume water, we have to consume food, right, to survive. But within that, there's quite a lot of kind of pathways to achieve that. And they are also very dependent on the society around us, right? So that's, and not just the society, our environment, right? And that's, I think, part of intelligence is coming up with these abstractions that, regardless of the environment, allow you to adapt, right, to these to the environment and be able to fulfill your fundamental desires. And those will depend on.
Do you want to run Llama efficiently on smaller GPUs? What if you could run both training and inference on the same GPU? With CentML's breakthrough optimization technology, you can maximize hardware utilization and slash AI computation costs. Running LLMs at scale shouldn't break the bank. CentML's intelligent optimization platform helps enterprises deploy AI models with maximum performance at minimum cost. Experience the difference.
I want to start with a brief introduction of what we've actually been working on. And we've been working on this PILE language modeling benchmark. The PILE is a big data set of natural language. It comprises a lot of different aspects or a lot of different tasks that you can frame in natural language. So this includes code, this includes math, this includes scientific papers, but also more general content that you could get from the web. And now this PILE language modeling benchmark is all about trying to learn language models that can predict the next token or the next word, if you will, in this big space of text. And this has really been around since early 2019. And the first models that were evaluated on this were GPT-2, and they were quite good at the time, quite bad now, if you look at them now. And what you evaluate here, so what you can see on this y-axis is called the bits per byte. That's really the next token prediction error. And what we've been able to show recently is that you can do much better than the previous state of the art by learning at test time. And I'll talk more about what that means. And you can do so with a much, much smaller model than the big models that were the previous state of the art. So the previous state of the art was a 130 billion parameter model. And now we're at 3.8 billion, so 30 times less, and actually much better. So I'm going to talk about how you can get this. And there are roughly two aspects to this. So one is really this idea of learning at test time. I'll talk about that first. And then I'll talk a little bit about some key aspect of that. And that is relating to data selection and sequential decision making. Cool. So what is learning at test time in this framework looking like? And I want to start with really a very simple picture. It's just the standard machine learning pipeline. You all know it. You start with some training data. You use that to train a model. And then you use that to make a prediction at some test instance. And now one of the first things that virtually everyone is taught in their first course on machine learning is that you should separate these stages of training and testing. You should train your model once on all the data. You should freeze it and then evaluate it, right? You should not conflict training and testing. But in fact, whenever you evaluate your model on some test instance, you know what you evaluated on, right? Latest before you do the forward pass, right? And learning at test time is really embracing that. So learning at test time is about using that test instance to train or learn a specific model tailored to what you're trying to predict, and then use that model to make a prediction. So I want to motivate this a little bit, like with a very simple picture of why could something like this even make sense. I want to talk about curve fitting. So let's say we want to fit this black curve, and it's just a linear curve, so the simplest curve you can come up with. And this is fairly easy, right? You can just use linear regression and do this, fit this, and be done with it, right? But what if you now want to fit this slightly more complex curve? Like, that looks a bit weird, and if we fit our linear regression, this will somehow capture the trend in that curve, but it will clearly not fit it so well. So a lot of machine learning has been about figuring out what methods can we come up with to get a better fit of that curve. And really one of the fundamental ways that people go about this is parametric models, right? You could increase your model class that you search over to extend kind of the feature space, for example, using polynomial features or periodic features to get a much closer fit here. Or you could use neural networks to learn these features from data, right? But what you do is you increase the model class, which means you have to search this much larger model class, and you need a lot more data, right, to do that. Now, another approach that people have looked at is non-parametric models. So these are kind of approaches where your model itself is the data. You don't kind of train anything on top. So there will be kernel regression, kernel-rich regression, k-nearest neighbor. For these, sometimes the problem is that really, if the data is large, this can be very expensive. I want to talk about local models. And really, very simply, it looks like this. So you train a kind of separate local model, in this case, still a linear model, for every prediction that you're trying to make, right? And you can see with this, I mean, just pictorially, you can fit this much more complex than linear curve, much better than just using the linear regression. So I want to argue that kind of these local models have fundamentally two components. So one, they have a parametric controller. So that is kind of the model that we use to make these local predictions. So in kind of the simple story that I've been telling, it would be a linear model, but you could go beyond that, right? And then the other key component is this non-parametric memory, or your data from which you select to build your model locally for every prediction, right? Traditionally, people have been using k-nearest neighbor in some representation space. So they build a representation space, and then for every prediction, they select the k-nearest neighbors to kind of your instance, to your test instance, and then build their local model using that. Now, I want to kind of take a step back and think about what these local models might mean. It seems kind of interesting that using the small model class, so sticking with these linear models, we can predict this much richer than linear function class. And another thing that seems kind of interesting is that just using one local or training one local model requires much less data than having to train this huge model that would fit this entire complex curve. That seems kind of odd and maybe too good to be true, right? And there are a few things that I didn't talk about yet. And maybe one of the key things is the importance of representations or kind of abstractions. And this really kind of, I think, comes up, especially when you talk about how you select data from this non-parametric memory. So to be able to kind of cheat and being able to just train a small model or search a small model class using few data, essentially how we could be able to cheat this way is by kind of leveraging abstractions, leveraging representations that tell us, okay, only this information is important of kind of the entire piece of information that is stored in your memory. Only these pieces of information are important, and you can focus on them, and maybe these abstractions already tell us how we can use them to make predictions, right? That's kind of very abstractly speaking. I'm going to go into detail more about how you could operationalize these ideas, but that's kind of the abstract theme that I want to go into. So I want to kind of motivate one more, like this problem of local learning in kind of a pictorial fashion. And to this, I want you to consider kind of this space as the space of all token sequences, and maybe this manifold in the space as this manifold that captures all of natural language. And then really what most of state-of-the-art models are doing is they're trying to learn this entire manifold or fit that entire manifold. And you could call that kind of some inductive type of learning. But then you realize quickly, okay, what you care about is not really all of natural language. You don't want to reproduce Reddit. Instead, what you want is you want to solve some coding problem, right? So you look into kind of the interesting part of natural language, maybe that's coding, and then you fine-tune your model, right? And local learning is really the extreme of that. So you realize, okay, actually what you care about is not all of code. You care about only a subpart of code, and maybe you just care about the specific coding problem that you're trying to solve with your code base, right? You give it your code base, you ask it your task, and it tries to solve that, right? So that's kind of the story of local learning and what it's trying to solve. And this idea is not really new. It definitely comes from at least the 60s and 70s. And I think in the 80s, this kind of famous statistician, Vladimir Vapnik, put it in a very nice way. He said, when solving a problem of interest, do not solve a more general problem as an intermediate step. Try to get the answer that you really need, but not a more general one. And I really like that quote. Essentially what he's saying is that you have some problems that you're interested in solving. And instead of trying to solve everything, every possible problem at once, of course, if you could do that, if you could solve every possible problem at once, you would also solve the problems that you're interested in as a byproduct. But I mean, that's infeasible. We have limited time, limited memory, limited compute. Now, instead of doing all that, just focus on the problems that you're trying to solve, actually, on the problems that you're interested in. And most likely, you can do that much more efficiently than if you were trying to solve all problems at once. So now I want to go back to LLMs and kind of stick with this kind of simple picture and this kind of curve fitting example that we talked about, and entertain the hypothesis that, let's say this more complex curve describes all of natural language. This more simple curve that somehow fits that trend, but not so perfectly, corresponds to current language models. Could kind of language models which locally learn at test time fit this curve more accurately without increasing the representational capacity, without increasing the model class, right? Sticking within the model class that we are currently using, but using that, doing this local adaptation at test time, can we fit that curve more accurately? So does this work? I kind of preempted that in the beginning a bit, and it does. So kind of here you can see results with a bunch of different models at different scales. I'll go into that a bit more. Essentially what we do is we do a very mild form of local learning at test time. So we just kind of select some data. I will talk about how we select that data. We select some data from this big memory and then do a few gradient steps. So do a few steps of backpropagation, 50, on that data, and then kind of use that as our final model. And that's kind of this red bar, and you can compare it to this gray bar, which is the initial model, and you can see, it's quite obvious, it does much better, right? And significantly better, and even, or kind of especially with the state-of-the-art model Phi3, just using kind of this local adaptation, local learning, gives you much more than going to this largest Phi3 model, which is the 14B model, more than 3 times as large. That gives you much less than twice as the gain, or maybe even more than doing this local learning. And then another thing that we looked at was comparing that to in-context learning. So in-context learning is also a form of local learning. So instead of doing backpropagation, what you do is you just put your data into the context window. And really, I will show you some results, really explanations for these results I don't really have, and we can entertain maybe some theories later. But interestingly, with these like GPT-2 models, doesn't work quite as well as backprop. With Phi3, it's more on par. But some really cool thing that we can do is, because we work with this pile data set, which is the big metadata set of human language, we can look more closely at where does this divide actually happen. And so these are GPT-2, GPT-2 large, Phi3, and just kind of the top 4 sub-data sets where you see kind of the largest difference between context and fine-tuning. And what seems odd is that across these very different models, I mean, especially GPT-2 and Phi3 are very different, it's very consistent where you see the difference between fine-tuning and putting stuff or data into context. So in particular with like math, this is like school level math questions, coding or free law are court opinions. So probably like more complex problems. There you see like a big advantage of using backprop instead of in context learning, at least with these models. And some other interesting thing is that with the math data set, so by the way, I should have said this earlier, these absolute numbers here are relative to the base model. So the percentage of kind of bits per byte that you have after you kind of do this local adaptation relative to the base model. So 100 is really the exact performance of the base model. 0 would be you predict everything perfectly. 50% would be kind of a 2x improvement over the base model. Interestingly, with math, you see that context, or kind of we found that in context learning, doesn't change the performance of the base model at all. Whereas using the same data, but backprop, can drastically improve performance. And actually the same story, interestingly, with archive. It doesn't show up in the top 4 here, but it's also kind of staying at 100% for in context learning. And with fine-tuning, it gets much below that. So that's kind of odd. So I just wanted to kind of highlight that, and maybe we can entertain some thoughts later. Cool, so now I want to talk a bit about this other kind of challenge, which is the challenge of what data should you actually select to build these local models. And that's really a key part, because if your data is not good, you will end up with a bad local model, as I will show you. And you really want this to work if you want to deploy this approach in practice, because if this doesn't work, then things can really fall apart when you deploy such a model. Because very differently from when you train a model at train time in the standard train-test split, here, you don't have control, right, when you deploy that inference time and don't monitor the prediction, every kind of prediction that your model makes, you really don't know what is happening. Versus in the standard train-test split, you can benefit from the fact that you just train your model once, then you have a lot of chance to probe it, see how it behaves, right? And then once you feel comfortable with it, you can deploy it, right? In this case, you're kind of adapting your model as it is deployed, and maybe that makes you a bit hesitant. So this is really a crucial aspect. I want to kind of motivate this kind of question of how should the kind of model make decisions of what data to select by this simple example. So let's say you are prompted, or the language model is prompted with a question about the age of Michael Jordan and how many kids he has. Now clearly kind of these are 2 pieces of information, and if the model has not remembered them, it needs to be somehow retrieved, if you will, from the data, from this memory. And kind of we ran this experiment with the setup that you don't know, or that you don't have kind of a piece of information that has these 2 data points in conjunction. So you just somehow have to synthesize multiple pieces of information. And the standard thing that people do is, as I mentioned, this k-nearest neighbor retrieval in some dense embedding space, in this kind of representation space. And what that does is, I can show it to you here, it retrieves 2 pieces of information that are both about the age, right? So that kind of failed. And why did it fail? It's because if you look in this latent space about kind of as to what is closest, it will pick up this dominant frequency. If you have multiple pieces of information that kind of have this frequency in high amplitude, it will pick these repeatedly before kind of going to different clusters that are slightly further away. And that's kind of a problem here. So it picks redundant data. So actually the total kind of information gain of these 2 data points is not so large. Of the first data point, yes, but adding the second data points doesn't really add information relative to what we're trying to predict. Now I want to talk about a different way of selecting data, and we call that SIFT. And in this case, kind of this finds this, kind of tries to select non-redundant pieces of information and gives you actually answers or the information necessary to be able to answer this question. And we see this effect not just qualitatively, but also quantitatively. So if you look at the next token prediction error, here against the kind of number of fine-tuning steps you do, you can see that selecting informative data makes a real difference. And if you just go by nearest neighbor selection, maybe in something like a well-maintained data set, like this academic PAL data set, right? While it's still significantly worse than SIFT, it's not completely bad, But if you go to maybe a more realistic setting where you have true duplication of information, and we simulate by just kind of duplicating data in the pile, when nearest neighbor would then repeatedly select the same data point, right? It's not able to detect if some information is actually redundant or not, then the error can actually blow up, right? And in that case, you don't want to do any local learning at test time if your error gets that much worse. So that's kind of interesting. Now, how does SIFT work? SIFT follows a very, very simple principle. This principle is simply to select the data that maximally reduces the uncertainty about what the model should respond to the prompt. And I will talk more about how you can operationalize this. It essentially requires 2 steps. So the first thing is we need to estimate this uncertainty, and then the second thing is we need to minimize it. So very simple. I will talk about both these things. So first off, estimating uncertainty, and that's a very difficult task, and a lot of people have looked at this in the context of large language models, but also many other models. And the way how kind of we approach this is we were somehow trying to make this tractable so that in the end we can optimize over this quantity, right? And to make this tractable, what we did is we kind of used a simplifying assumption. So what we did is we treated the language model as a linear model, right? So a linear model not in the kind of values of the distribution, but a logit linear model. So the logits, before they are passed through the softmax to give next token probabilities, is kind of assumed to be linear in some known representation space. So of course, this representation space can be highly nonlinear in the actual inputs, but we assume it to be known, and it's an unknown function. And this may seem like a very strong assumption, but interestingly, since kind of the beginning of language models, people have looked at how language models may encode concepts as linear representations in this kind of highly nonlinear representation space. Some recent work kind of at ICML was really kind of showing this very nicely. And kind of people have been calling this the linear representation hypothesis. And a lot of work in interpretability, for example, is also using this idea. And similarly, if you look more like to data selection, and for example, comparing it to k-nearest neighbor, fundamentally, these methods that are relying on dense embeddings extracted from LLMs are also kind of somehow relying on this assumption, fundamentally, right? They're also kind of treating or looking at this fixed representation space. So what does this give us? We can kind of make sense of kind of these 3 key objects. So the first one is being the ground truth. So this is kind of the true distribution of natural language. And then we assume we have some pre-trained model. So that's the base model that we start with. And then we kind of denote by Sn the fine-tuned model after taking these n gradient steps. And what we show is that you can relate the error. So this here is the error of your model after taking these n gradient steps. You can relate this to some key object that I will talk about. So how do we measure this error? This error is here kind of the TV distance, the total variation distance between these 2 distributions over next tokens. First off, the true distribution and then our model, right? So if this error is small, then we're very happy, then we have a good language model. If this error is big, then our language model is screwed up somehow. And now what we can do is we can, under the simplifying linearity assumption, we can bound this by some scaling factor, which depends also kind of on the performance of the initial model, and this key object sigma n, which just depends on your prompt. And this key object, in that sense, is kind of a measure, or can be interpreted as a measure of how uncertain the language model may be about what it produces as output to the prompt. And the cool thing is that under the simplifying assumption, this object is actually tractable. So we can analyze this analytically, and we will also be able to minimize it. And this object kind of depends on the representation space that you have, and also on the data, right? If you have good representations, you can make sense of the data better. That's why it depends on that. And of course, it depends on the data, right? If you have good data, you can make better predictions. You can be less uncertain. If you have bad data, you must be uncertain. So how can we, or how do we minimize this uncertainty? So again, the principle was kind of to choose the data that minimizes uncertainty of the model after having seen that data. So how do we kind of operationalize this? We just minimize this kind of uncertainty about the answer to the prompt, given xn. Xn is just the kind of data that we have selected so far, plus the new data point, right? So very natural object. And I'm going to talk more about that in just a moment. You can actually interpret that in various ways. What you can actually show for this type of selection rule is that the uncertainty decays. The uncertainty essentially vanishes to some kind of irreducible constant. And I'm going to walk you through this. So what this shows is that kind of as n grows, as you select more data, your uncertainty decays to this irreducible constant here. And what is this irreducible amount? It's kind of very intriguing because it depends both, again, on the abstractions and also on the data that is available in your memory. So what you can think of is that if you have a memory that kind of tells you about, let's say, sports, right? And then you get asked a question about politics, and your model does not have good knowledge of politics, you won't be able to answer the question well. And that is essentially what this says. So it says that you both need to have the data in your memory to be able to answer the question, and you also need to have the abstract representations to be able to make sense of that data. And those two things are really critical in conjunction, right? So essentially it says that predictions can only be as good as the data and the learned abstractions. Cool, so I want to kind of give you a little bit of a different interpretation of what SIFT does from a probabilistic lens, because I think in that way one can very well describe kind of what its properties are and also contrast it from what nearest neighbor retrieval does. Because again, as we discussed, nearest neighbor retrieval really doesn't take informativeness and especially redundancy, possible redundancy in the data into account. And kind of this probabilistic lens will allow us to really emphasize why SIFT does this. So what I want you to think about is the following. I want you to think about the language model as a probabilistic model, which has a belief over what is the right kind of model that describes natural language. So this belief is like an epistemic belief, kind of a probability distribution. So this controller is kind of like has this epistemic belief, and now it interacts with this memory. It searches this memory for some data, and then receives a response, a noisy response from that memory, and updates its beliefs, right? And then it searches again. And what you can show, or what is a fact, is that SIFT actually maximizes some neutral information, some information gain in this probabilistic model. And what is this information gain? SIFT maximizes the information gain of the data or of the response that it receives from memory relative to the prediction that it's trying to make, conditional on all of the data it has seen so far, right? And that's really kind of a very simple statement, right? So you can express SIFT kind of very succinctly. What is kind of nice about this interpretation is that you can write this information gain in a different way. So you can split it into two terms. And the first term is just the information gain of your response from your memory, of your data, relative to the prediction that you're trying to make. And that is maximizing your relevance of the data that you're trying to obtain. And you can think about this as the thing that nearest neighbor search optimizes, right? It's just trying to find the most relevant data. And in a needle of a haystack thing, that's maybe not the worst thing if you're just searching for something. But if you're learning, you need to synthesize multiple pieces of information together. And this is kind of conveyed by the second term. So the second term is also called, it's actually called redundancy in information theory. It's also called the multivariate information gain. So what this term measures is it's measuring the redundancy of your new response, y of x, and the previous responses, y1 through n, relative to making this new prediction. So in that sense, it's really, it's very large if your information, new information is redundant, is already contained in the previous information, and it's very small if your new information is novel. So we're trying to minimize that, right? So you're really trying to get novel information. And in that sense, really this kind of decomposition tells us why SIFT works, why SIFT selects non-redundant data as opposed to nearest neighbor retrieval. Awesome. So does it actually work? And does it work better than nearest neighbor retrieval? It does, again, on all scales. So here we also compare it against something that's called uncertainty sampling, which is more like purely about minimizing redundancy and not really so much about relevance. So it turns out that actually balancing these two things in an intricate way really helps. And interestingly, this helps a lot more with stronger base models. So here, I mean, relative to the performance gain kind of nearest neighbor retrieval, SIFT does add something, but not so much to GPT-2 than it does to Phi-3. So that indicates, and it's kind of intuitive, that if you have a stronger model, it is more important for that model to receive maximally informative data to make use of that than a weak model, where maybe actually some redundancy is not so bad to make a better prediction. And another thing that we find that I'm happy to talk more about is also that we find kind of larger gains over nearest neighbor retrieval if you increase the size of the memory. So it seems like if you have a larger memory, taking informativeness into account is also more important. And one other thing that I want to point out, and that's maybe also very important, is that we see that this performance improvement over nearest neighbor retrieval is robust across all of the pile, right? So regardless of what subdomain of natural language you work on, it seems like taking this informativeness into account always helps. And in particular, if you look at this kind of column that corresponds to this failure mode of nearest neighbor, where information is duplicated, where pretty much always your fine-tuned model is worse than the base model, really SIFT achieves a kind of dramatic improvement. Awesome. So I want to zoom out a bit before we end and talk about one more kind of thing in this kind of context of learning at test time that I find really exciting and kind of a very interesting question. And that is, can we learn these representations over time? It seems very important that if we want to end up with like open-ended systems, that these systems are not held back by the abstractions and representations that they have learned once, but that these systems continuously adapt and continuously learn from kind of new interactions, new data, actually the compute that we spend, right? It should not go to waste. And I've said before that these representations and abstractions are really key to making good predictions. So I want to, again, motivate this by a very simple sketch. So let's say the black dot corresponds to the test instance that we're trying to predict. And these gray dots correspond to data that is needed to make a good prediction, right? And this kind of shape here is supposed to somehow demonstrate in our simple Euclidean space how our model thinks this black dot and these gray dots are related. So good abstractions would put these gray dot very close proximity to the black dot. But these representations are not good, right? So what we want to end up with is a system that over time can move these gray dots that are bad representations closer to the black dot. So over time improve these representations as we encounter maybe bad representations and as the model learns. And really something that is astonishing to me still, and was astonishing to me back then when I found this, was that bootstrapping these representations somehow worked or works. And actually, when I did this experiment first, this was one of the first experiments I did when I was working on this project, and that really motivated me to look into this deeper and see, okay, why is this actually working so well? Was this, and I'm going to tell you all about it. So the setup is we're working with MNIST. So MNIST is this data set of handwritten digits. So digits 0 to 9, and you're trying to classify what is the digit. And now in this setting, we were not aiming to classify all the digits. We were just trying to classify, I think, the digits 3, 6, and 9. And we started with a simple convolutional neural network, randomly initialized, very straightforward. And then we trained this neural network to make these predictions. And we tried two ways of training it. So the first way was just take this data from this kind of training data set of MNIST, IID, so kind of the normal way, and that's this dashed line. And then the second approach that we tried was to take the data from this data set in a non-IID fashion. Instead, take the data to maximize this information relative to the predictions that we're trying to make. So what I discussed earlier. And that is the solid black line. And you see, I mean, it's quite obvious it does quite a lot better. But it seems odd. Why does it do better? Because we don't have some magical information that tells us that certain data is more relevant, more informative than other, right? Because we started with a randomly initialized model. Initially, the first data that kind of this non-IID method selects should be roughly random, because there's not much there's really almost no information encoded in this model. So interestingly, while the first piece of data is basically random that we select, now we train that model on that first piece of data. So what you can think about, this model gets better predictions, but also its representations get slightly better, right? They're not perfect after seeing one data point, but they get slightly better. So the next time we select data, we see slightly non-random data. So data that is slightly more informative than random data. And that repeats, right? We update the model on that, and then we get slightly better representation still. And I think that is kind of maybe the main reason why we see this big difference between these two curves. And that's really encouraging me to say, okay, maybe we can scale this up. Maybe we can end up with truly open-ended systems that can learn representations over time, improve their representations to make better and smarter decisions, to learn more at test time, or to end up with better predictions. So we scaled this up. We also did this with C4 which is just more complex images, larger data space. We didn't start from random, but we started from some kind of pre-trained model that was pre-trained on ImageNet, but with a random head, and kind of saw the same effect there. So I wanted kind of to highlight this. I think this is really a key aspect to making really open-ended systems work, is to not train them once and then maybe do this local adaptation on top, but actually let kind of the learning mechanism itself learn over time. Cool, so I want to wrap up, and I'm really looking forward to interacting with you guys already. So what I kind of talked about today is I was trying to contrast these local models that solve one problem at a time to inductive models. And these are kind of most state-of-the-art models currently. And these try to solve all problems at once, at least all problems that you can specify in a certain domain. But if the domain is human language, you can specify a whole lot of problems in human language, right? If you try to solve all of these at once, that is bloody hard. And it seems kind of interesting to me, it's kind of an interesting hypothesis that local learning allows allocating compute to places where it is interesting. And sort of as a compute allocation mechanism, I think it's quite a nice thing to think about. Cool, I think that's everything. I'm happy to talk to you afterwards. Thanks.
So yeah, before food, we have some time for questions. So, which is the CFAR 10.
Yeah. 100.
What's your split in terms of all the classes versus all the classes?
I think it's 10%. So 100 is all the classes. We looked at 10 classes. So we try to just learn it for 10 classes out of the 100.
Okay, did you try different splits? But yeah, here the big idea is that all the data from the other classes
basically irrelevant. We didn't try other splits actually. But I think you would probably see a similar effect. Of course, if you get closer to 100, you see much less of a boost. And if you have a smaller if the information that you're trying to extract from the memory is more sparse, then you will gonna do much better than random, right? Because random is just gonna take a lot of pieces of information that is actually irrelevant relative to what you try to predict.
Have you tried using this in models like diffusion models for image generation, and what happens there?
Very good thing. So we are working on something like that. So that is actually something that I also find very intriguing, is that kind of this general framework, while kind of historically speaking, this has been around for a long time. Recently, with kind of in-context learning, this has entered people's minds. So now when I talk to colleagues, for the first time about this project, they are all saying, are you doing context learning, right? Because in kind of the current, I think, kind of mindscape of people, kind of this local adaptation is very much linked to context learning, because this is the kind of the way in which people have seen this local adaptation approach to work recently with large models, that kind of this emergent behavior comes up where models can learn from what you put into their context. But it seems interesting that with models that are not autoregressive, so that don't have a context window, like a diffusion model, you could probably do something similar. And certainly not through in-context learning, because they don't have a context. So yeah, it's definitely a very good observation.
Yes, I was just asking, very early on you had the comparison between different model sizes and their perplexity. What's the chunk size that you used for the local learning there? Like, what's the split?
For like the stride, you mean, or?
Yeah, like how local is the local learning?
So correct me if I misunderstood your question, but you're asking kind of how local, kind of what is the size of this local neighborhood around the test instance that we try to learn this data manifold, essentially. That's a very good question, and it's a very intricate question, actually. We are essentially, so kind of as a proof of concept, we are just taking a fixed amount of neighbors for every data point. So we're just taking 50 neighbors and then just doing a single gradient step on all of these. But actually, in practice, you wouldn't want to do that, right? In practice, you would want to train on a different amount depending on the question, right? If you get like a prompt to a chatbot that says hello, you don't want to do any local learning. If you get like a very complicated question, but you don't have any data in your memory that can help you with that, you don't want to train at all. But if you actually can improve your response, then you would want to train. And so in practice, what you want to do is you would want to do this adaptively, depending on your memory, depending on your model, and depending on the kind of problem that you're faced with. And this also adapts then to kind of, I think what I read out a little bit of your question, that if you have, I don't know, you have some parts of your data manifold where your memory is very sparse, and you have some parts of your data manifold where your memory is very dense, right? If you do this with a fixed amount of kind of compute for everything, you will cover much larger neighborhoods on the data manifold where the data manifold is sparse, and you will cover much smaller neighborhoods where the data, where kind of your memory is dense. And what we actually looked at, what I didn't talk about at all, what we looked at was to do this adaptively. So you could think about these uncertainty estimates as actually being useful to telling you, okay, here we actually have information in our memory. Here we don't have information. Like this irreducible term may even be useful to tell, okay, here for this response, we're able to make a better prediction than for that other response. And so what we were also looking into is kind of, can we, in a sense, reduce compute cost by just kind of terminating local learning early for those points where, let's say, the data manifold is sparse, or I mean, your memory on the data manifold is sparse, or different cases where you don't learn so much. Yeah.
Question, like, what's the intuition around how you scale this for much larger models and much larger data sets? Because the biggest issue was like in the single-digit billions.
Yeah. I mean, it's really tough to do in an academic setting, like to go to multi-digit billions. I think actually right now the single-digit billions are quite good state-of-the-art models, and actually the kind of best open source state-of-the-art models are in the single-digit billions. So I mean, there's these Llama 3.2 models which just recently came out, which are quite good, and so on. I think, of course, there's always some kind of hypothesizing going into whether this also works with larger models. I am actually quite stoked by the fact that it worked on the scale of GPT-2, and it worked pretty similarly on the scale of Phi-3. And Phi-3 is not like a bad model. Phi-3 is really state-of-the-art, very close to a very good model. And I mean, on this one plot, I also put Gemma 227b, which we didn't fine-tune, right? But we also evaluate kind of the zero-shot version of that. And that was also doing much worse than the fine-tuned Phi-3. And it seems like if you go to a larger model, clearly your error is going down, but it's going down at a certain speed. Right? And what kind of this local learning does, it's really opening up a new way of spending compute that is kind of orthogonal to the way of spending compute at train time. So, and of course, it's hard to say, like we didn't do the experiment yet, whether it would also improve the performance of, let's say, GPT-4o. But I think, yeah, I'm relatively positive that to some degree it will.
So when you were explaining like about representations and making them more general, you mentioned that like initially we start with selecting random points, and then these points slightly become to be less random. And I was thinking about balancing exploration-exploitation through maybe the lens of mutual information, like and if that's, you think, like maybe a semi-accurate description of what you're doing, like did you think about parallels between your work and similar works done in reinforcement learning, or if you could draw ideas from there, because it's a bit similar to, like, philosophically at least.
Yes, I would say yes and no. I mean, in some way, kind of these kind of pure search methods have also been entertained, let's say, in kind of the context of reinforcement learning, where you don't have a reward signal and you just try to, let's say, learn the dynamics or learn the dynamics, learn the environment. But usually then you don't have this exploration-exploitation trade-off, right? Because that arises from kind of the necessity to balance kind of exploring and then kind of exploiting and doubling down on what seems promising. So I think it doesn't really, like mathematically, it doesn't really arise in the same way. In the representations context, I do think that on some level there is a kind of exploration-exploitation trade-off there. So I would agree with you on that. And I don't think actually what we are doing currently is kind of accounting for that adequately. And there's definitely, I think, opportunity to look into that more.
I separated this like information tier, mutual information into these two terms, where one was capturing redundancy and the other was capturing relevance.
Yeah.
I thought that could be like this redundancy could capture randomness and the relevance could capture exploitation somehow.
Yeah. Okay. Yeah, I think that is an interesting interpretation. I don't think, like in the literature, people talk about it in that way, but maybe philosophically, I think philosophically one can think about it that way, as like relevance being somehow exploitative, like, or finding information that is exploiting, and this diversity term or this non-redundancy term trying to make you explore. But yeah, I think fundamentally, like mathematically, deep down, these things are still a bit different. But it is on its own an interesting kind of dynamic that if you want informativeness in the data that you select, you need to do both, like both relevance and diversity. And that's definitely very interesting. Yeah.
Well, I have one question on like the open-endedness part. Because for instance, in the like last experiments that you do on like the Cypher 100, so you basically said that you only like train on like a subset of the classes, right?
Yeah.
And like I was wondering, like regarding of like open-endedness, if you then like also like try to like once the model like learned like the like classes that you were trying, should like try to like expand like the to also like other classes as well, and also maybe like regarding like the LLM part, if you could also maybe like expand like the memory as well, like while you like train.
Yeah, very, very good questions. For the first question, we didn't try that. I think it would be interesting. Generally, I think about this kind of local learning as happening in two stages. Like there's an inner loop and then there's an outer loop, right? Or it's like similar to the idea of fast and slow weights. So you have kind of fast weights that are changing at test time, and then you have slow weights that are changing on the outer loop. And you are kind of resetting the fast weights sort of always when you're faced with a new task. And in that way, I would probably try to just reset the model and do this kind of local learning before you then focus on different classes, instead of kind of leaving off where you kind of focused in on these new tasks. It's like, I don't know, philosophically, I like to think about it, you know, you are kind of working hard on solving this one problem, you're focusing your brain on that, and then you're kind of taking a break, you're trying to delete all that and kind of have new space to put new stuff in. Of course, there's some mixture of those things going on, but that's why I like to think about it in these kind of two levels, like an inner loop and an outer loop. And then, what was the second question again?
Like, for me, like LLMs, like similarly, what you can do is that you can like somehow
increase the memory.
Yeah, exactly.
We didn't try that. What we did try, we tried to do it with smaller memory. Of course, we couldn't increase our memory because our memory was bounded by kind of the data set of the pile. And we didn't do this dynamically, so we didn't like dynamically for every question adjust it, but I don't think that really makes like really an impact, because essentially you can think about every test instance that we're testing here as IID coming from this pile distribution. And what we see here is that I didn't plot the kind of absolute performance improvement over the base model. What I plotted here is the relative performance improvement over nearest neighbor selection. So kind of 100% is doing exactly the same as nearest neighbor selection. And anything that goes below is you're doing better than nearest neighbor selection. And what seems interesting that if you have, like, as you get larger memory, yeah, this informativeness is more important. Like, I didn't plot it here, but you see the same thing also in absolute numbers. That you, of course, if you have a much larger memory, you will be able to essentially kind of do better. And I think what is really interesting here is that kind of this SIFT thing, or also these representations, are kind of allowing us today to search this really large memory very efficiently. And essentially, you can parallelize this to no end. So I think you can, people have done this at internet scale. Right? This is really, you can scale this memory up to include kind of almost every artifact that humans have ever kind of produced. And that would still run fairly quickly. Yeah. Thank you.